Okay, we know that there are these four fundamental subspaces associated with each matrix, right? Um, and earlier we saw what these four fundamental subspaces mean. Right? We know that the column space is the linear combination of the columns of A. The row space is the linear combination of rows A. Null space is essentially all the elements X that get mapped to 0. And the left null space is essentially the null space of A transpose. Okay? The column space is the set of vectors that you can produce by doing AX. You can choose any X you want. All the possible vectors that you can produce by doing this operation is essentially represented by the set CA. Okay? And any X that you choose that produces AX, some element in C of A, can be thought of as composed of two components, a row space component and a null space component. XR, XN. If you multiply this out, XN, this is from the null space of A. This is from the row space of A. We know this is equal to 0 because it's from the null space. That means this, if this was some B, right, which belonged to the column space of A, that means AXR is also equal to B. And of course, this belongs to the column space of A. That means no matter what X you choose here, you can write it as sum of two components, one in the row space, one in the null space. The part of X that gets mapped to the non-zero value B is the element, is the component from the row space. Okay, the other component goes to 0. In addition to these properties, right, another interesting property is that the four fundamental subspaces are mutually orthogonal, especially two of them, okay, or pairs of them. The row space and the left null and the null space are subspaces of Rm, given assuming A is n cross M. The row space and the left row space and the null space are orthogonal. Similarly, the column space and the left null space, which are subspaces of Rn, they are orthogonal as well. In fact, they are not just orthogonal subspaces, they are orthogonal complements, because the sum of these two subspaces will produce all of Rm, and similarly, some of these two subspaces will produce all of Rn. That's all. There's nothing else to say. And of course, because XR belongs to A transpose, Xn belongs to null space of A, XR transpose Xn. What can we say about this? Because the column space and the row space and the null space are orthogonal complements, can we say about this operation? The standard inner product of the row space component with the null space component. Yeah, 0. This will be 0. That's because E of A transpose is perpendicular to N of A, or in fact, C of A transpose whole perp equals N of A. Means the row space is the orthogonal complement of the null space of A. Okay, right. What else? Yeah. All the orthogonal values are zero, is what you mean? When the set of vectors is not linearly independent. When you project one vector onto the subspace spanned by the previous orthogonal columns, the difference comes out to be zero. Is that what you're saying? Okay. What do you not understand there? Or what is bothering you? We did a couple of examples. No, we'll do one. It's fine. The QR code is also not uploaded, is it? Video? No. Oh, okay. Two things. The videos are available in Teams. Yeah, you're right. I forgot about that. In Teams, you can go access the videos. It says the YouTube version might not be uploaded yet. Yeah, it's not been 60 days. So at least the lectures about QR code, and QR decomposition and stuff is should be available. If you just go to Teams, no, they're not in Teams. Great. Okay. All right. Yeah. So if it's not uploaded, please. Sorry, you should just come and inform us. Yeah, we might have just forgotten. Yeah. Let's do the QR decomposition of this. This is our matrix. What is the first step we do? What is the first step? Yep. What is Q1? A1, is it? A1 is what? 111. Right, okay. What is this? Yeah. This is easy. What about how do we get A2 now? Q2 now? Yeah. I don't know the value. You'll have to tell me. What is it? Q2. Two. Hey, are you sure? Q1 and Q2 have to be orthogonal. Are they orthogonal? This is not correct. So the first thing you do is find out the orthogonal projection matrix onto the subspace spanned by Q1. Now we find the E2 vector, which will be A2 minus E1 A2 will be 110 minus 1 by 3. So what you told me is not Q2. That is the orthogonal projection of A2 onto the subspace spanned by Q1. But you have to find the difference, right? That is what is orthogonal. 2, 2, 2. The difference is 1 by 3, 1 by 3 minus 2 by 3. Okay. Now E2 does not have length 1. E2 is orthogonal to Q1, but E2 is not of length 1. So Q2 will be what is the length of E2? Yeah, square root of 2 by 3. Like this. 3 is outside the square root, right? What will that be? Okay. Yeah. Is that of length 1? Are you sure it's the square root of 2 by 3? Will be 1 by 3 square, 1 by 3 square by 1 by. Hey, the square root is all over. Is this okay? That's of length 1. Is Q2 orthogonal to Q1? Yes or no? No, just do it. Don't stare at the screen. Just do it and tell me if you're not immediately able to figure out. See, many times these questions, if they stump you, just do the calculation. You have the numbers. I'm not asking you an abstract question. You can just do the computation and find out. Hey, how will you find out if Q1 and Q2 are orthogonal to each other? What should be 0? Yeah, standard inner product should be. I don't know why you're so hesitant to say it's standard inner product should be 0. Compute the standard inner product and tell me if it's 0. Then it's orthogonal. Is the inner product 0? No? How do we compute the standard inner product? So we need to find out if Q1 and Q2 are orthogonal to each other. So you do Q1 transpose Q2. Q1 is 1 by 3, 1, 1, 1. We need to take the whole transpose. Q2 is 1 by root 6, 1, 1 minus 2. The scalar can come out, so it will be 1 by 3. The column vector will become a row vector. The 1 by root 6 can also stays out, so I'm going to put the root 6 here. 1, 1 minus 2. The scalar remains the same. How do we compute the inner product now? Yeah. Great. Is it 0? Why did it take so long to compute the standard inner product? See, I'm puzzled. It's just multiplication of numbers and addition of numbers, right? Why? Yeah. Root opposite, is it? What do you mean? So you did Q2 transpose Q1, is it? Hey, but how will that give you a different answer? Okay, here it's 1 into 1 plus 1 into 1 plus 1 into minus 2. Yeah. Yeah, maybe ಇದೆಲ್ಲ போட்டது better. UPS line connect பண்ணது better. Just call those guys and change it. Wrong. Yeah. So if you take the inner product, it's 1 into 1 1 into 1 plus 1 into minus 2. So that will be 0. If we did the other way around, it will be 1 by root 6, 1, 1 minus 2, 1 by 3, 1, 1, 1. The scalar will come out to be the same. It will be the same. Okay, all right, sure. So they are orthogonal. Okay, now let's compute Q3. How will you compute Q3? What do you need for computing Q3? Okay, so to compute Q3, we need to first take A3 and then orthogonally project it onto the subspace spanned by Q1 and Q2. To compute the orthogonal projection of A3 onto the subspace spanned by Q1 and Q2, you need the orthogonal projection matrix P2. Okay? You can do it two ways. You can find out P2 if you have an orthonormal basis for the subspace spanned by Q1 and Q2. Q1 and Q2 form an orthonormal basis because they are of length 1, they are mutually orthogonal to each other. That means if I take Q1, Q2 and compute this, don't be stumped by this. This is simply, if you remember, if you have an orthonormal basis for a subspace, and if you take those, let's say U1 to UL, form an orthonormal basis for some subspace S. If you form a matrix U with U1 to UL as the columns of that matrix, okay, and remember this is a orthonormal basis. U transpose will be an orthogonal projection matrix onto the subspace spanned, onto the subspace S. Okay. Here, my matrix U is simply Q1, Q2 because Q1 and Q2 form an orthonormal basis. This is U. This is simply U transpose. Okay. If you expand this out, it will come out to be Q1 transpose plus Q2 transpose. So to compute P2, you don't have to do the entire multiplication again. We've already found out what is P1, Q1 transpose. That's this matrix. All we need to do is compute Q2 transpose and then add it to P. So this is P1 plus Q2 transpose. So all we need to do is compute Q2 transpose. What is Q2 transpose? So that'll be 1. So because it's Q2, there'll be two 1 by root 6s. So that means I can write it as 1 by 6. And then I'll have a column vector 1, 1 minus 2 multiplied by the row. What will this be? This will be 1 by 6. And what will be this equal to? And P1 we know is 1 by 3. 1, 1, 1, 1, 1, 1. 1. We'll simply have to add Q2 transpose here. Shall be 1 by 6. You need to tell me what the elements will be. Sorry? Q2 transpose. Okay, what is it? Row or column? Are you telling me the row or the column? Row, okay. 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 So this will be 1, 1 minus 2, 1, 1 minus 2, minus 2, minus 2, 4. Okay. Now tell me what will be P2. What is it? Is there a common scalar that we can take out or no? Always. Okay. 3 is it? 3, 0. Okay. All right. Now that we have P2, the next step is to find out E3. E3 is, oh, the next step is to find out E3, which is A3 minus P3, A3. What is A3? A3 is 101. 1 minus 3, 3, 0. 1, 0, 1. In all of this, I'm just doing the algebra, but you should keep thinking about the geometry. How you do Gram-Schmidt. A1, you normalize it to be Q1. You have A2, you project it down, and then you get E2. And then if you normalize this, then you get Q2. If you have a third vector that's pointing out of the plane, then you project, find this error, normalize its length, that's Q3. So that you should never forget. Algebra is algebra, but the most important thing that you get out of this course is the geometrical intuition. What is E3? Yeah, it's all 0, is it? Is that what you get? Cannot be all 0, right? Because the first one is 1 minus half. Yeah, tell me what is it? Yeah, 0. Okay. Now that E3 is not 0, right? What does it say about A1, A2, A3? Well, A1 was not 0, so A1, the set A1 is a linearly independent set. When you estimated Q2, E2 did not come out to be 0. Then what does it say about the set A1, A2? Well, because the error did not come out to be 0, so E2 was not equal to 0. That means the set A1, A2 forms a linearly independent set. Now, E3 has come out not equal to 0. What does it say about the set A1, A2, A3? The set A1, A2, A3 also forms a linearly independent set. Okay, now, okay, that means we can find Q3. What is Q3 now? Yep. So, why is it? Okay, 1 by root 2. Okay, what is the difference between 1 by root 2 and root 1 by 2? Is the 1 by 2 in the square root? Okay, just tell me the vector. It's fine. You don't have to say anything else. What is the vector? If there is a scalar, tell me the scalar. And then what is the vector? Q3. Here? Inside, is it? Hey, you're telling me the same thing. It's supposed to have length 1, right? What is the length of here? What is the length of E3? What is the length of E3? Just compute it. 1 by root 2, is it? 1 by root 2. Okay. So what will be Q3 now? What will this be equal to? See, for many of these things, you don't even need my approval, yes or no. You can just verify it yourself. If you come up with a vector, it has to be of length 1. If it's not equal to length 1, then you know you've done a mistake. For this, this will simply be 1 by root 2. That's all. Okay. Instead of length 1, you can verify if I've done a mistake. Yes? Sir, how is it written by 4? Okay. Uh, it's 1 by root 2 minus 1 by root 2, 0. So the norm of this will be square each term, add them together, and then take the square root. Square of 1 by root 2 is 1 by 2. Square of minus 1 by root 2 is also 1 by 2. So it is length 1. Okay. Is Q3 orthogonal to Q1? And is it orthogonal to Q2 also? So that you can verify by either computing Q1 transpose Q. We know Q1, Q2 transpose Q1 or Q1 transpose Q2 is 0. Is this equal to 0? This, of course, this should be equal to and is this. Both of them are 0. First one is 0. Second one is 0. Okay, first one. Okay, yeah. So Q3 is orthogonal. So now, before we proceed, right? The columns of this matrix A are from R3. Okay. How many vectors can you take from R3 and form a set so that that set that so that the set that you form is linearly independent? Can you take one vector from R3 and form a set? And is it possible for that set to be linearly independent? Yes. If it's not 0, then yes, it's a linearly dependent set. Can I take two elements and form a set? And can that set be linearly independent? From R3. As long as the two vectors are not collinear, the set will be linearly independent. I can take two non-collinear vectors in R3. What about, can I take three vectors from R3? Well, if it's three vectors, they cannot be coplanar or collinear. That you can do. You can take two vectors and then take a third vector that's out of the plane formed by the two vectors. So I can take three vectors and still be linearly independent. Can I take four vectors and be linearly independent in R3? You cannot. Okay, that was the first module where we said you can only take n vectors from Rn and still expect to be linearly independent. The moment you take an n plus 1th vector, for sure you're linearly dependent after that. Okay, now the columns are all from R3. We've got three vectors here, and we did the QR decomposition. The error did not go to 0. That means these three vectors form a linearly independent set. The moment now I take a fourth vector from R3, I know for sure I'm going to be linearly dependent. 0 we know is a problem. If you compute E3, E4 will come out to be 0 because it'll be 0 minus 0. Let's forget about this, right? Let's call this A4. Now let's find Q4 using A4 and see what happens. So you'll essentially now have to find out P3, right? The orthogonal projection matrix, which is Q1 transpose. We know Q1 transpose and Q2 transpose. In fact, the sum of this is P2. It'll simply be P2 plus Q3, Q3 transpose P3. Tell me what is P. You'll simply have to compute Q3, Q3 transpose, and then tell me what is P3. Add it to P2 and tell me what is P3. What is Q3, Q3 transpose? Do you have it? What is Q3? Q3 is, well, there'll be two 1 by root 2, so there'll be 1 by 2. Okay? So I can just write it as 1 by 2, 1 minus 1, 0, multiplied by 1 minus 1, 0. What do you get? It'll be half 1 minus 1, 0, 1, 0. This will be minus 1, this will be plus 1. Yeah. So that's Q3, Q3 transpose. Let's add that to P2. P2, what is P2? P2 was this. Right? It was 1 by 6, 3, 3, 0, 3, 3, 0, 0, 0, 6, plus 1 by 2, 1 minus 1, 0, minus 1, 1, 0, 0, 0, 0. Let's simplify this. So this will be half, half, 0, half, half, 0, 1, plus half minus half, 0, minus half, half, 0. What will that come out to be? You got the identity matrix. Isn't it weird? you computed an orthogonal projection matrix and it came out to be the identity matrix. It didn't happen for P1, it didn't happen for P2, but it happened for P3. Well, we were computing an orthogonal projection matrix, right? Onto what subspace? When you were computing P1, what subspace were you projecting to? No. Subspace. The whole of the space in which we are working is R3, but the subspace onto which we were projecting when we computed P1 was the subspace spanned by Q1. What was the subspace we were projecting to when we computed P2? Yes, it was the subspace spanned. So first was Q1, second was Q1. Well, they're orthogonal. The subspace spanned by Q1 and Q2, and then you had Q3. What is the subspace spanned? So P3 is the subspace spanned by Q1, Q2, Q3. What is the subspace spanned by Q1, Q2, Q3? Well, three vectors linearly independent from R3. What should be the subspace? Well, it's all of R3, right? If you have n linearly independent vectors from Rn, they will span all of Rn because they form a basis. Okay, that means the subspace onto which you are projecting is the entire space. So if I take any vector from that space, it's in that subspace. And we know whenever you project a vector onto a subspace S, if you take a vector from the subspace S and do the orthogonal projection of that vector onto that subspace, you will get the same vector. That means your projection vector will the the projected vector will be equal to your original vector, okay? As long as that vector is from that subspace S. But here, when you have three linearly independent vectors from R3, the subspace is all of R3. So no matter what vector you take, if you orthogonally project it back to R3, you will get the same vector. That is why your projection matrix is I. It essentially means it's the same vector. There is the orthogonal projection operation is trivial. Right? Okay. So what does it tell me about E4? E4 is A4 minus E4 A4. Well, you don't have to do too much computation. Sorry, P3. P3. I'm sorry, not P4. Well, P3 is I. So P3 A4 is A4. So this will be A4 minus A4. That means this vector is linearly dependent on the previous where the previous three vectors. In fact, here I've not assumed any numerical value for A4. A4 could be any vector you want. It didn't have to be -1, -1, -1. It could have been any vector and you would have gotten 0. That's because the first three vectors already max out all possible vectors you could take and form a linearly independent set. There is no more vector you can take from R3 and still be linearly independent. You have to do the same thing again. Oh, fine. Okay. Let's just change this matrix a little bit and redo the whole thing. Let's do the QR decomposition of this. Tell me what will be Q1. Q1 is easy. Q1. No. The length is not 1. You have to normalize the length to 1. That's all. This will be 1 by root 3. That's fine. We've got Q1. Now we need to find the orthogonal projection matrix P1. What is P1? There'll be two 1 by root 3, so I can take that out. 1, 1, 1. Be the matrix. Okay. Be all ones. Now tell me what is E2. So from this we find out E2. Can you tell me the abstract expression? What will be E? How will you compute E2? Sorry, A2? P1. That's fine. Okay. So that'll be what is A2? A2 is 1, 0, 1 minus 1 by 3, 1, 1, 1. 1. And oh, that is, oh, I see. Yeah. Yeah, but that switches off. No, it does not switch off. You're right. Wait, which line is the UPS line, you know? What is it?
Which one? Which one?
We'll find out. It's my We'll find out. Running out of charge, I think. Okay. What is it? Hey, hold on. Which vector is 2, 2, 2? Are you talking about this? Oh, it's... Ah, yeah, that's okay. Yeah. Tell me what is E2? You have it? What is it? 1 by 3? 1? Okay. Is that of length 1? Well, we don't know, but let's still normalize it anyway. Q2 will be E2 divided by length of E2. What will that come out to be? One by root 6, is it? Here, 1 by root 6. Okay. One to one. Is this orthogonal to Q1? Well, here you don't even have to consider the scalars. Forget the scalars. It's 1, 1, 1. That means you simply add all the elements. If you add all of the elements of Q2, you get 0. So it has to be orthogonal. Fine. That's Q2. Now let's find out P2. You don't have, how will you compute P2? It will be P1 plus Q2, Q2 transpose. What is Q2, Q2 transpose now? There will be 1 by 6 out. 1 minus 2, 1. 1 minus 2, 1. Be 1 by 6. Tell me what the matrix will be. One. Okay. All right. So that will be then 1 by 3, 1, 1, 1, 1, 1, 1 plus 1 by 6, 1 minus 2, 1 minus 2, 4 minus 2, 1 minus 2, 1. What will be P2? One by 2, 1, 0, 1. Zero. Okay. Now we find E3. What will be E3? What will be the expression for E3? What is A3? A3 is minus 1, 1, minus 1. P2 is half 1, 0, 1, 0, 2, 0, 1, 0, 1 multiplied by 1 minus 1, 1 minus 1. What does that come out? Are are the are the columns A1 and A2 linearly independent? A1, A2. Forget about A3 now. I'm going back one step. Why? not distance. What is not 0? Yes. Not the p-value. E2 did not come out to be 0. That means A2 and A1 form a linearly independent set. Okay. Now we are finding out E3. Okay. Zero. That's weird. Okay, what does it mean then? What does it tell me about A3? No, no. Okay, what is not linearly independent? A, no. Okay, linear independence only applies to a set of vectors. Are you saying the set formed by A3 is not linearly independent? No, A3 is not 0. So the set only containing A3 is linearly independent. Linear independence applies to a set of vectors. So if you say only A3, right? A3 is not 0. It's in fact minus 1, 1, minus 1, 1, minus 1. So the set A3 alone is linearly independent. Because in this procedure where you started from A1, A2, A3, and then when you reached A3, your E3 turned out to be 0, means the set A1 formed by A1, A3 is not linearly independent. In fact, in the first step, we found the set A1 was linearly independent. When we tried to compute Q2, E2 was not 0, so we could compute Q2. That implies the set A1, A2 is linearly independent. But when we tried to compute Q3 from the set A1, A2, A3, E3 was 0. That means this set is not linearly independent. A1 and A2 are. The moment you add A3, the set becomes linearly dependent. That means I can express A3 as a linear combination of A1 and A2. Okay? That's what this means. Okay? If I had taken a different A3, let's say A3 was 1, 2, 3. Okay. Now tell me, now let's compute E3 for this. So this will be the new A3 minus E2, A3. I've only changed the third column. I've replaced this with 1, 2, 3. Okay. So now, so P2 does not change. So I can just do the same computations. That will be 1, 2, 3 multiplied by half 1, 0, 1, 0, 2, 0, 1, 0, 1, 1, 2. What is it? Minus 1, 0, 1 is it? I don't know if it's correct, but it looks like it's a non-zero value. What does this tell me now? The set A1, A2 was linearly independent because the A1 was not 0, E2 was not 0. Now, the moment I add this new A3, now I ask, is this set linearly independent? What is the answer now? This is not equal, E3 is not equal to 0. That means this is linearly independent. That means I can find a Q3. Okay, all right. I hope that clarifies things. Okay, let's do the QR decomposition of A, the final last A. E45. What is Q1? Yep. What is then? What is Q1 Q1 transpose? Okay. That's my P1. Now I compute E2. To compute E2, I do A2 minus P1. A2. Sorry. Huh. It's exactly equal to A2. When would that happen geometrically? When A2 equals E2? What coincides with the same line? Okay, let me draw. This was A1, right? From this, we found out Q1. Now, when you did A2, when you computed A2, from with A2, you tried to compute E2. E2 came out to be equal to A2. When would that happen? A2 is very good. Okay, let's try that. You're saying when A2 is in the span of A1, right? Okay. If since A1 is a single vector, the span of that vector will be of the form alpha times A1, correct? Okay, all right. Let's say A2 was like that. We don't know what is the alpha value, but let's say our A2 was alpha times A1, which would mean it's alpha times 300, which means it's 3 alpha 0 0. Okay. Compute E2 for this A2. This will be I'm asking you to do this because you said I asked you what is the geometric picture when E2 comes out to be equal to A2. You said when A2 is in the span of A1. So if A2 is in the span of A1, it has to be of the form alpha times A1. This you agree, right? Span of a single vector is simply scaled versions of that. So A2 has to be some, we just don't know the alpha. Now if you assume A2 to be like this, and if you compute E2, let's see what we get. What do we get? So this will be, just do the computation. This will be 3 alpha 0 0 minus P1 times 3 alpha 0 0. What do you get? The result is 3 alpha something. What is it? Hey, hold on. What is the final answer? When you do, what is E2? Just tell me what is E2. Zero is definitely not equal to A2. So E2 is definitely not equal to A2. So that answer is wrong. But does it make sense that it's zero? When will zero happen? When you compute this error, when will it be equal to zero? Huh? Linearly? Yes. In fact, what you said was, when you said A2 is in the span of A1, you're saying the set A1, A2 is linearly dependent. If the set is linearly dependent, the error will be equal to zero, not A2. The only way the error will be zero and it will be equal to A2 is A2 itself was zero. So A2 is not zero, so that answer is out. So it is not in that line, right? Okay. What other option is there? Where A2 equals E2. In general, see, in general, A2 looks like A2 is like this, right? If you remember the picture, right? This is A2. And then we drop a perpendicular. I don't know if it's visible. We drop a perpendicular. This vector is P1 times A2. What is E2 here? Where is the vector E2 here in this picture? Not the space. It's this vector from the tip of P1 A2 to the tip of A2. That's your E2 vector. E2 equals A2 minus P1 times. Now the question is, when will, so if A2 and E2 are equal, geometrically, when will that happen? Sorry? Exactly. When A2 is perpendicular to A1. In fact, you can verify if the inner product of A1 and A2 will be 0. Right? Because 3 times 0, 0 times 4 plus 0 times 0, that's 0. When A2 is already perpendicular to your vector A1, E2 will be equal to A2. That means your implies that Q2 is simply either E2 divided by norm of E2 or E2 divided by. See, remember, the purpose of this entire step is to find a normal, is to find a vector that is orthogonal to the vectors that you already have. Because A2 was already orthogonal, this error just comes out to be the same as A2. That's all. And this step where we are multiplying by the length is simply a normalization step. That does not do any orthogonalization. This step here is what does the orthogonalization, and the second step is simply normalization. What will this be equal? What will Q2 be equal to now? Well, what is the length of A2? Length of A2. Length of A2, 4. So what will be A2 divided by length of A2? Right. Now let's compute E3. Without computing E3, can you say anything about E3? Or, sorry, A3 is it? Okay, why is that? Sure, but that does not mean anything to me. Okay, geometrically, when will E3 be equal to A3? Perpendicular to what? Both what? Yes. When your third vector is perpendicular to both the previous two vectors, then E3 will be equal to A3. In fact, the previous two vectors form a plane. So if the third vector is orthogonal to that plane, then E3 will be equal to A3. Because you can see that, right? For example, the way we find E3 is this is A3. It's not perpendicular to the plane. You drop a perpendicular, and the E3 vector will be this vector, right? from the tip of the projection to the actual vector. And that vector will be equal to this vector when this is perpendicular. And in fact, you can verify that inner product of A1 with A3 is 0. Inner product of A2 with A3 is 0. That means A3 is orthogonal to the subspace spanned by A1 and A2. That means E3 must be equal to A3. What does it tell me about Q3? What will be Q3 now? Yes, that's all. In fact, here I chose diagonal elements to make it easy, but it doesn't have to be. We can try another. Maybe here it's immediately clear that they are orthogonal to each other, but maybe we'll try another example. Here, tell me what is Q1? Yeah, see, doing the algebra is important. Knowing how to do the algebra is important, but always make sure you're able to connect it back to the geometry. That's the real value of this whole exercise. Just doing the algebra, you will never do the algebra. The computer does it for you. What you need to know is what the algebra means, at least geometrically. Yeah, this is easy. 1, 1 minus 1. So let's compute P1, which will be Q1, Q1 transpose. There is a 1 by root 3, so I can take, there'll be a 1 by 3, this I know. What will be the matrix? One, 1 minus 1. Okay, now let's compute E2. So this will be A2 minus, correct? That is in fact equal to A2. What does it tell me about A1 and A2? Yeah, A1 and A2 are perpendicular to each other. Okay, that you could have very well verified by simply doing the inner product between these two. And in the inner product will be 0. You can verify. Okay, right. So what will be Q2 now? Yeah, okay. Now let's find out P3. Sorry, P2. P2 will be P1 plus Q2. Q2 transpose will be equal to 1 by 3, 1, 1 minus 1, 1, 1 minus 1, minus 1 minus 1, 1, plus 1 by 2. Okay, great. Okay, now tell me what is P2. The scalar is 5 by 6, is it? First element is 5 by 6. Are you sure? It will be 1 by 6 now. Just verify. Because it's minus 1 by 3 plus half. Yes, yeah. Next. Next one is easy. Next row is easy. What about the last row? No. Yeah. Hey, always remember orthogonal projection matrices are symmetric. That means you only have to figure out the diagonal element. You know the other two elements already. 1 by 6, is it? Yes, it has to be 1 by 6 because this is 1 by 6. What is this element? No. It is symmetric. These two have to be the same. 5 by 6. Okay, all right. So that's P2. So now let's compute E3. E3 will be A3 minus E2 times. One by 2 is it? Okay. Inside. Yeah. Minus 1. Well, this is not equal to A3. What can we say then? All we can say is it's not orthogonal to the plane spanned by A1 and A2. What can we? But A2 was of course orthogonal to the line spanned by A1. From this, we should be able to find out Q3. What if it had been like this? What if A3 had been does that work? No, it does not work. I have to do a little bit more work. It's fine. In fact, I'll ask you this. What if A3 had been what would be E3 then? Yeah, I'm sorry. Sorry. -1. Okay. Before that is what is Q3? Tell me that first. For this E3. √3/2. Okay. Yeah, that's the length. Right? Okay. So that'll, if you divide it by the length, it'll be right. Is Q3 perpendicular to Q1 and Q2? Just verify that, please. It is Q1 transpose Q3 is 0. Okay. All right. Q2 transpose Q3 is 0. Q2. This is Q2. Q2 Q1. Zero. Okay. So yeah, Q. That's fine. Now, what if A3 was like this? What would be E3? Instead of A3 being 1 minus 1 0, what if it was 1 minus 2 minus 1? Okay. Yeah, so E3 will be A3 minus T2 A3. I'm asking for this new A3. One by? You sure? Okay. Okay. A3 is 1 minus 2 minus 1. P2 is, I can take the 6 outside. Okay. Be 5, 2, 1, 1, 2, 2 minus 2, 1 minus 1 minus 2. 5 minus 4 plus 1. 2. 2 minus 2. 1. 4 minus 5. 2. Where did I go wrong? I went wrong somewhere. We've done a mistake somewhere, I think. Because if this is correct, right? A3 is simply a scaled version of Q3. That means Q3 is perpendicular to both A1 and A2. In fact, it is orthogonal to A1 and A2. So this has to come out to be A3. We've done a mistake somewhere. It's probably in this matrix. You got it? You got A3, right? Oh, maybe I've done a mistake. So, yeah, that's the point I was trying to make. But of course, when A3 is orthogonal to both A1 and A2, in a non-trivial sense, if it's the diagonal element, if it's the diagonal matrix, right, then it's trivial. If you had a matrix like this, 1, 1, minus 1, 1, 0, 1, 1, minus 2, minus 1, if you just look at it, it's not clear that the columns are orthogonal to each other. But if you do, when you do Gram-Schmidt, when E3 equals EI equals AI, that means the vectors are all mutually orthogonal. Yeah. Okay. All right. You figure out where I did a mistake? Ah, really? Okay. 5 minus 4 minus 1. That's 0. Oh, yes. Yes, you're right. 0. Okay. Yeah, 0. Yeah, I'm stupid. Yes, this will all come out to be 0. I'm sorry. Yes. That will be 1 minus 2 minus 1. Yeah. Okay. All right. That's all. Okay. I hope that clarifies questions about QR decomposition. Tomorrow we'll start the new module on matrix inverses. Thank you.